Hello, everybody. My name is Akihiro Takigawa. Also with me is Jack Murphy, my co-presenter. We are both students at Williams College. Today, we will be speaking about extending virus dynamics to K-level star-like graphs. This is a project that we have been working on in a small REU program at Williams College under the supervision of Professor Stephen Miller. So why are we interested in virus behavior? There are many applications of this in several fields, the first of which is epidemiology. Modeling the way that viruses spread across geographical regions would perhaps allow us to predict this. This is of particular interest in our current day and age in the middle of the COVID-19 pandemic. However, there are other fields in which our topic would be of interest. For example, interactions on social media could perhaps be modeled in a similar way, which would be of interest to computer scientists. In looking at a model, there are some questions that we would like answered. The first question is there a steady state? Or in other words, does the model stabilize to some sort of standard behavior? If so, what are its characteristics and what can we interpret from this? The second big question is, can a model be expanded further to better capture real-world phenomena? These are the questions that we started off with in conducting this project. The model that we looked at is called an SIS model. There are two states that each node on a graph can take, either susceptible or infected. If a susceptible node contracts the virus, it transitions to the infected state. If an infected node is cured, it transitions back to its susceptible state. We are particularly interested in the behavior of this model on star-like graphs, graphs that have a central hub node that is connected to a number of spoke nodes. No spoke nodes are directly connected with each other, with each having only the hub node as its neighbor. This type of graph is interesting because it can represent the connections between geographical regions realistically. For example, the central hub node can be a large city, while the spoke nodes are suburbs surrounding it. Our model has 4 parameters. Beta is the probability that an infected node infects its neighbors, and delta is the probability that an infected node is cured. Zeta sub IT is the probability that node I is not infected by its neighbors at time step t. And 1 minus p sub IT is the overall probability that node I is not infected at time step t. As you can see, the latter 2 parameters are mutually recursive. I would like to now introduce the previous work into this topic, off of which our work is based on. Becker-Greaves tunnel, among others, previously explored this model on 2-level star-like graphs, which has one central hub node connected to a number of spoke nodes. They showed that under this model, given enough time, all spoke nodes converge to the same probability of infection, allowing them to simplify the model to one that has 3 parameters. A, the probability that an infected node is not cured at any time step. Beta, which we relabeled as B for simplicity, and finally N, the number of spoke nodes. Their main result was the following. There is a critical threshold, 1 minus A over the square root of N, for which if B is less than or equal to, the virus dies out, and above which the probability of infection iterates to a non-zero number. So a natural question to ask is the following. Can their work be extended to a 3-level star-like graph, where there is a central hub connected to each spoke, but each spoke also acts as a hub to a number of higher-level spokes? We call the first level of spokes 2-level nodes, and the second level of spokes 3-level nodes. If so, could this be generalized to a star-like graph with an arbitrary number of levels, in other words, k-level? This is the question that we tackled in our work. Our basic approach was to start with a 3-level case, and then see if this could be extended to the k-level case. Here is the system we are looking at. Because we are using the same model, 2-level nodes have the same behavior, and 3-level nodes have the same behavior. Hence, this system can also be simplified as before, with an additional parameter n sub 2, the number of 3-level spokes. Because we have 3 levels of nodes, including the central hub, we have an additional variable z for the probability of infection of 3-level nodes. The main result of our investigation is as follows. Similar to the previous two-level case, there exists a critical threshold for which the virus either dies out or has a probability of infection that stabilizes at some non-zero value. The first step was to find what the infection rate stabilizes depending on B. To do this, we looked at fixed points where the values that the system returns, given some input, does not change. But even our simplified model is still complicated to analyze, so we instead look at partial fixed points, where one of the three variables remains unchanged. To do this, we introduce the functions phi1, phi2, phi3, where respectively x is unchanged, y is unchanged, and z is unchanged. We can explicitly solve for these, and they turned out to be functions that are tractable to analyze. To get the phi functions, we set each variable to what that variable becomes under our system f and solve the resulting equations. The lower half of the slide is what we got. However, these functions turned out to be in 3 dimensions, which is hard to work with. So we analyzed the intersections of phi1 and phi3 and the intersection of phi2 and phi3. The intersection of these two composite functions would then be the complete fixed point. Graphing this with various values of b, we get the above diagrams. From left to right, b is less than a threshold, b is at the threshold, and b is above the threshold. As you can see, in the former two, the origin is the only fixed point, while in the latter, there is an additional non-trivial fixed point. We proved through some algebra and arguments in concavity that these are the only fixed points that are possible in our model. Now that we have our fixed points, an educated guess will lead us to think that depending on whether b is above or below the threshold, the infection rate should stabilize at one of these 2 points. We first focus on the case that b is below the threshold. We found that when b is below the threshold, the probabilities of infection of the central hub node, the 2-level spoke nodes, and the 3-level spoke nodes all iterate to 0. In other words, the 3-tuple x, y, z iterates a trivial fixed point under f. Our basic argument is that all points inside the region x greater than phi1, y greater than phi2, and z greater than phi3, which we call region 1, all iterate to the same trivial fixed point. Then we can draw a cube with one corner being the trivial fixed point and the opposite corner being some point in region 1. By showing that this point in region 1 goes to a trivial fixed point when we take the limit as the time step t approaches infinity, we can use Squeeze's theorem to say that all points inside this cube iterate to a trivial fixed point as well. By taking larger and larger cubes, we can conclude that all points iterate to a trivial fixed point when b is less than or equal to a threshold. Here are some diagrams showing the slices of region 1 on the xy plane at different values of z. As you can see, when z equals 0, phi1 and phi2 intersect at the origin, meaning this is a fixed point. To prove this, we need some preliminaries. First, we showed that points in region 1 are strictly decreasing x, y, and z on an iteration by f. Next, we showed each iteration always stays in region 1. Finally, because a trivial fixed point is a lower bound for values of x, y, and z, we use the monotone convergence theorem on the sequences generated by x, y, and z under f to show that they all converge to 0. So any point in region 1 iterates a trivial fixed point in our model. Now that we know this, we can prove this for all points. We first consider our cube. We assume that one corner is a trivial fixed point, the opposite corner is a point in region 1. Because we know that the coordinates of the opposite corner is strictly decreasing in x, y, and z, the image of the cube under f is contained in the original cube. Because we know that the opposite corner, that is in region 1, iterates a trivial fixed point, our cube shrinks on iteration by f, with all points inside it approaching the trivial fixed point. As we can take larger and larger cubes to encompass all points, This is formally a proof by induction. We can now conclude that all points iterate to a trivial fixed point by f when b is less than or equal to a threshold. I will now hand it over to Jack for the case that b is greater than a threshold.
Okay, so now that we have shown that when b is less than the critical threshold for a 3-level star graph, that the initial configuration will eventually evolve to the trivial fixed point, which is the origin, we'll now move to show that the other side of the coin, when b is greater than the threshold, that we have any non-trivial initial configuration will evolve to the non-trivial fixed point. So this is our theorem here, and the argument for this case will be very similar to the previous case where b is less than the threshold for a 3-level star graph. So this time, instead of having just one region that is sort of in the upper part of the 0, 1 cube, we will define region 1 to be where x, y, and z are less than their respective phi functions, and then region 2 to be where x, y, and z are greater than their respective phi functions. And note that in our previous case, we labeled region 1 to be essentially what we are now saying is region 2. We just did that to keep you guys on your toes a little bit, I guess. So now doing this, our approach from here out will be to consider a cuboid with one vertex being closest to the origin in region 1, and then another corner of the cuboid being furthest from the origin in what would be region 2. And then we shall use the squeeze theorem to show that any point inside of the cuboid will exhibit the same limiting behavior, essentially meaning that all points inside a cuboid, essentially covering the entire 0, 1 cube, will iterate to the non-trivial fixed point. So here's a bit of a visualization of how we might view region 1 and 2. And these are slices of the xy plane at different z values of 0, 0.25, and 0.75. And for this particular configuration, where we have the number of level 2 nodes being 6 and the number of level 3 nodes for each level 2 node being 10, this particular configuration, you can see that as z is getting bigger, the intersection of the phi functions of x and y are converging up here to close to where x equals 1 and y equals 1. Okay. So now here are some key lemmas that are needed to prove that when b is greater than the critical threshold, the system will iterate to the non-trivial fixed point. So firstly, points in region 1 will strictly increase in x, y, and z on iteration by the function f, which controls the dynamical system. So what we might imagine that being is all the points that are close to the origin are going to be increasing towards the upper corner where the upper corner of 0.111. And similarly, points in region 2 will be strictly decreasing in x, y, z. So the points up high will be coming towards the origin, and they will hopefully be meeting somewhere in the middle. So the next lemma that's important is that any points inside of region 1 will iterate inside of region 1 under f. And similarly, the same holds for region 2. So any points starting in those regions will stay inside throughout the entire evolution of the system. And then all non-trivial points in regions 1 and 2 will converge to the trivial fixed point under f. And that's kind of resulting from the previous two lemmas. And now once we have these lemmas, we can consider such a cuboid, assuming the vertex close to the origin is XL, YL, ZL, the vertex furthest from the origin, XU, YU, ZU, and respectively in regions 1 and 2. Then the image of this cuboid under F we find is strictly contained in that cuboid, meaning that when we iterate the entire cuboid, every point in the cuboid every point will be contained inside of the original cuboid. Thus, what we have then is, because of our previous lemma that the corners iterate to the fixed point, and since all points iterate inside of the image of the cuboid, we have that all points will converge to the non-trivial fixed point. So now let's try to extend this to the k-level star graph. So recall that for level 3, this is our function that controls the dynamical system. And for the k-level, it's very similar. And specifically, for, the first function controlling the x values is essentially the same, and also the last function controlling the k-level. The only thing that is a little different are these middle functions here. Okay, but again, they have essentially the same shapes, which is very nice. So now our goal is to find what might the fixed points be. We're going to take the same steps as before, looking at the partial fixed points and taking the intersections of the phi functions. So the key lemmas to show the existence of fixed points is that phi1 is always going to be convex, whereas phi k is always going to be concave. And then all the phi functions in between will be both non-decreasing and concave. However, they turn out to be functions of 2 variables instead of 1, whereas these are 1 variable. However, it turns out that the composition of a concave function of 2 variables down to 1, that is non-decreasing, and a regular concave function of 1 variable is also concave. What this means is that we essentially can take the composition of all the functions of phi sub k all the way down to phi sub 2 by our lemmas, by knowing that when we compose consecutive functions, the resultant will be concave. And then by induction, we can show that the composition of all these functions turns out to be concave. Now, to complete the analysis, we also recall that phi1 is convex. And so because of that, it works out essentially the same as the level 2 case, or the level 3, or the level 2 and level 3 case, in that we have the existence of a fixed point due to the intersections of a convex and concave function. So as for limiting behavior, it also will work very similar to the level 3 case, as we shall see. And actually, how we'll proceed is, instead of using a cuboid as we did in the level 3 case, we'll use what we might call a k-dimensional orthotope, which essentially means that we are going to extend the dimensionality of the cuboid to the k levels, and then prove that this geometric object will converge into either the non-trivial fixed point when b is greater than the threshold, or when b is less than the threshold, that the system or the sequence of these geometric orthotopes will converge to the origin, the trivial fixed point. And this is our theorem of that right there. And as for future work, this current model is very good for virus propagation behavior where there is a central hub. That is just by the very kind of geometry of the graphs we are working with, the star level graphs. So As we can see here, like the New York metropolitan area might be well represented by that. But what about if we want to consider regions where there are several large hubs all connected together? Then we might want to try to, instead of having a single hub in the middle of the graph, we might want to start off with a complete graph, such as what you might find in the Northeast Corridor. And then each of these hubs in a complete graph would themselves sort of emanate out a K-level star graph. So that is the future direction that the virus model could be taken. And that is the conclusion of our presentation. We would like to especially thank our advisor, Stephen Miller, and we would also like to thank our support from the Small REU 2020 and Williams College. Thanks very much for tuning in.